In the previous video, we have already discussed static position error constant, where the static position error constant tells us the performance in terms of a steady state error of a unity feedback system when a unit step input is given to the system. We have already discussed how the effect of static position error constants to different types of system, type 0, type 1, type 2, and higher. In this video, we are going to discuss another type of static error constant, which is referred to as static velocity error constant. Similar to what we did in the previous video, we are going to evaluate the steady state error of a unity feedback system, but in this case, when a unit ramp input is given to the system. So in this case, the steady state error can be calculated using the final value theorem, just like what we did in static position error constant. Steady state error will be equal to limit s to 0 s over 1 plus gs times rs. But in our case here, rs is a unit ramp, and unit ramp in Laplace domain is equal to 1 over s squared. Therefore, the steady state error of a unity feedback system when a unit ramp input is given will be equal to limit s to 0, 1 over s times gs. Now, if I define a new variable that I call as static velocity error constant, or kv, where kv is equal to limit s to 0, s times gs, I can immediately rewrite the steady state error due to unit ramp input equal to 1 over kv. So in this case, the steady state error because of unit ramp input will be inversely proportional to the static velocity error constant. Remember, in here, the term of velocity error is not referred to a steady state error in velocity, so it's not an error of velocity, but rather to an error in position due to a ramp input. Okay. Now let's check how the static velocity error constant will look like for different type numbers. Because for type 0 system, n in the open loop transfer function will be equal to 0. That means we don't have pole that is equal to 0 in the open loop transfer function. Since there is no term s here for type 0 system, the static velocity error constants, if you just substitute 0 to all of the s's here, will be equal to 0. While for type 1 system, we will have one pole that is equal to 0 in the open loop transfer function. If you evaluate it, the static velocity error constant will be equal to the gain of the open loop transfer function. So in short here, for type 1 system, we will have a finite static velocity error constant. While for type 2 or higher system, because we have more than one pole that is equal to 0 in our open loop transfer function, the static velocity error constant kv will be equal to infinite. Now, how this will affect the steady state error because of unit ramp input? We have already discussed it in the previous slide that steady state error of a unity feedback system when a unit ramp input is given is inversely proportional to the static velocity error constant. Therefore, since the static velocity error constant of a type 0 system is equal to 0, the steady state error because of unit ramp input will be equal to infinite for type 0 system. While for type 1 system, we will have a finite steady state error here if, again, a unit ramp input is given to the unity feedback system. Similarly, of course, for type 2 and higher, we will have a zero steady state error when a unit ramp input is given. Okay, so to conclude again for this short video in static velocity error constant, type 0 system is incapable of following ramp input. So if you have a unity feedback system where the unity feedback system is considered as a type 0 system, meaning that we don't have pole that is equal to 0 in the denominator of the open loop transfer function. If you give ramp input to a type 0 system, the output will not be able to follow the ramp input. The output will behave something different than the ramp input. While for type 1 system, if we give a unit ramp input to the system, to the unity feedback system, we will have a finite positional error. This error is proportional to the magnitude of the input and inversely proportional to the gain k. So if a unit ramp input is given to a type 1 system, if we give a unit ramp input like this, the response still can follow the input. The response still can follow the unit ramp input, but let me change the color first. But the response will be, I don't know, probably something like this at the beginning because we have a transition at the beginning, but after sometimes it can follow the input, where the error here will be finite. On the other hand, if you have type 2 or higher system, the steady state response will be able to follow the ramp input perfectly with zero error. Meaning again, if we have a steady state, if we have, let me change the color again. If we have a ramp input given to a type 2 or higher system, the response probably will be something like this. At the beginning, it is still in the steady state condition, in the transient condition, sorry, but after some time, it can follow the ramp input perfectly with zero steady state error.